Well, folks, today is the day that we complete equation 2, this full model from this paper we've been looking at. We already have the overall harmonic oscillator well. We have a driving force acting on one of the particles. Ours is colored white. We have a damping force on all of the particles, robbing energy from the particles to the surroundings. And we have a bonding force between our particles, all three of them, with bonds turned on and off by this matrix. Currently, this matrix is switching between ones and zeros based on a uniform probability. What we're going to do now is implement a variable probability that's a function of the distance between the two particles that we're looking at. So this is the moment at which we implement this formula here. And I'm very excited. Let's take a look at what we've got here. Currently, we've got this as a we've got this probability as a constant. It's been 1%. It was pretty fun to watch. What we're going to do now is we're going to set up the calculation of this probability flipping rate here. Let's see, so we're going to call that R, just because that's what it's called over here. Actually, let's call it rate, since that's what it is. It's, oh no, I can't call it that. That's a claim function. All right, we're just going to call this R. This is going to be the rate of bond transitions. That sounds fancy, doesn't it? Actually, this is just the bonding rate, isn't it? But the more descriptive you are, the better. All right, so I need a constant out in front. Let's have that constant be... I think let's have that constant be 1 for right now, since we're scaling our probabilities in terms of 1. We can change that if we need to. So I need an exponential function, please. Exponential of negative. I need Aij of delta x. Okay, so I need to make a function here. This is going to be let's call it EA of, let's call this particle list of I underscore particle, comma, particle list of J underscore particle. And actually, we just need the positions of these things. Let's make that dot pause and dot pause. Okay, so we'll make that its own function elsewhere. So I've got EA, blah, 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 divide by KBT. So we're going to divide by Boltzmann's constant times the temperature. Close up that paren, close up that paren. Okay, so that means I need to define a few things. First, I've got to define this function EA, and then I've got to define Boltzmann's constant and the temperature. Let's take care of our constants here first. So let's have Boltzmann's constant be 1. For simplicity's sake, it's usually best to make your fundamental constants 1, and then you figure out what the units have to be thereafter. And our temperature, let's have that also be 1. Okay. And so we can change that when we want to make the system hotter or colder. Okay, so now we need to define this, this function here, this EA. Let's do that. Where shall we do that? Let's do that. I believe you can do that anywhere. Let's do that up at the top. So let's see. So we're going to call this defining EA of some stuff. And we're going to call this one, so I don't have to call these fancy, these long names anymore. I can just call this R1 and R2, right? So we're going to define EA of R1 and R2. And this is where we get into what this thing is. So here I need to implement this thing. So let's see, I'm going to need a 1/2. I'm going to need K bond. Oh, I should actually make an equation, have an equal sign. How about that? 1/2 K bond. Now I've got K bond defined down here, so I'm going to have to make that a global so that this function can access it. Global K bond. And then up here, I just put in global K bond. And that means when I'm in this function, it's going to access the same value for K bond inside this function and outside of it. 1/2 K bond And then I need the distance between, oh, oops, excuse me, I'm looking at the wrong thing. So this thing is actually this piece up here, my bad. Well, that's okay. We'll just call this one E12. That's a temporary value. So E12, because we're going to need that. So this is E12 equals 1/2 K delta x squared. So I need the difference between them squared. So I'm going to need magnitude of R1 minus R2 quantity squared. All right, so I've got 1/2 K x squared, 1/2 K x squared, minus some constant. Okay, so minus, call it eps for epsilon. Let's put that down with the other properties. So let's see here, global K bond, global epsilon, eps is equal to, let's make it something small, 0.25. Yeah, there we go. And what that does is it just gives, it just changes the depth of the well here. So here they are unbounded, here they are bounded, bonded. Here they are unbound, here they are bound. And so that's just the difference between those two. So that's my E12. So in order to get this EA thing, I also need this B term. So let's set up this B function here. B is going to be equal to. Now they've got their function for that on the next page, and they have that as K delta x squared. So technically that cancels a little bit with this thing, but we'll keep it separate because they do have, they do say you can change it. For right now, let's just use that. So let's have K bond times, go, this thing squared. Cool, like we had before. And so now my EA is just going to be, let's go back to the paper one more time. It's going to be B minus E12. So I've already got my B calculated here, B minus E12. And we're going to say return EA. So when we call this function, it's going to take those two vectors as inputs. So this is the, do they give a name for this? Is the height of the transition state barrier separating the bonded and unbounded. So I guess we'll call that the transition barrier. There we go. See, you do. We can use the word transition. They used it. I get to use it too. So let's see. I've got E12 equal 1/2 K delta x squared minus epsilon. E equals 1/2 K delta x squared minus epsilon. I've got my B equal to K delta x squared. Down here, I've got my B equals K delta x squared. And I've got my EA equals B minus E12. EA equals B minus E12. Cool, so we're going to return that EA. So when this thing down here calls for that, down where? Where did it go? Here it is. So when this thing calls for that, it's going to say, okay, R is equal to exponential negative EA of these two things. So this is a function of these two particles, positions, divided by KB temperature. Divided by KB temperature. Okay, so this is now going to replace that constant 1% that we had before. So this is now a varying probability based on the separation of the particles. So when the particles are closer together, they are more likely to bond than they are if they are farther apart. And same thing goes for them breaking a bond. So the closer they are together, the easier it is for them to get over this bump and end up bound. And the closer they are together, the closer they are together, the harder it is for them to get back over the bump because they have to go from here up to here. All right, I'm going to leave that as the same. Something's telling me I need to have a different probability of them to go from bound to unbound because of this difference in the height. But I'm going to leave it as is for right now, and I'll do some more research on that off camera. And I'm sure I will hear corrections in the comments starting now. Let's run this thing, take a look at what it looks like. Cool, so we're getting our bonds turning off and on pretty consistently, it looks like. Which is suggesting to me that yes, I probably do need to make that a different transition rate from one to the other. The advantage, though, being, the nice thing we have, though, is that they are kind of settling out to something of an equilibrium state, right? So these two have kind of fallen into the same pattern that we saw before, but they're being pulled back and forth by this thing. So even though the bonds are flickering on and off, the thing does result in some pretty consistent behavior, which is cool. Let's see what happens. Just to play around with this a little bit, let's see what happens when we increase the strength of their bonds. So let's go from a 0.5 to a 0.75. So this is now 3/4 the strength of the external harmonic oscillator potential. Right, and so now they're going to follow each other more quickly because the bonds are stronger. We're still losing energy to the damping force. But we still get a pretty good steady state here toward the end, so that's cool. Okay, let me do one more thing. Let's make the bond strength stronger than the harmonic oscillator potential. Here we go. Yeah, they're flying back and forth more strongly. They'll still level out to a steady state because of the damping force. I think it's taking them longer to get there, though, so that's cool. Yeah, so we kind of get the same kind of steady state behavior. So the white atom is kind of dragging the other two behind it, basically, because of the bond between them. Okay, cool. So I think that's a good stopping point for today. What I'm going to take a look at off camera is whether I need to have this probability, oops, wrong way, whether I need to have this probability here be different for turning the bond off than for turning the bond on, because now that I'm taking another look at this graph, I see that it should be more difficult to overcome to break the bond than it should be to form the bond. So I'm going to take a look at how we might implement that. But in the meantime, feel free to download this code, play around with it, let me know if you get some interesting results, and I'll see you next time. Bye-bye.